After all these introductory comments, I want to start with the first real content chapter of the course. And despite aiming for the physics, simulations, and physical models, including physical priors, it's nonetheless very important to start with the kind of this purely data-driven, supervised approach. I have a first example here that I think very nicely illustrates the challenges and problems. So it's actually one you can find in this web book. It should illustrate where one pretty common problem in using these methods, right? Obviously, as mentioned before, all these deep learning techniques can be extremely powerful. But if we apply them naively or in the wrong way, then they can be very wrong, often also very surprisingly so. So this image here on the left-hand side shows a learning target. So it's kind of just a parabola, but to make it a bit more interesting, it's basically one along x. So we're looking for a solution where some value, y square, is mapped to an x. So for a certain point here along the x-axis, maybe our 0.6, we're looking at which number squared gives us a 0.6. So it's still really just a parabola, but it's not a function, it's a map anymore. And then the solution would basically be square root of 6 plus and minus, right? So we have two solutions due to the square. Still a very simple setup. The only slight difficulty here is that basically both positive and negative solutions are allowed. And if we now generate data from these solutions and feed that to a neural network, maybe some of you can imagine what happens. We have averaging. So we want a network that given an x gives us a solution. There are always two solutions. In this case, nicely symmetric, right? They're plus minus for every point of input. This will average out. Your solution will be 0. You might notice this in the loss, that it does not converge to a very low error, but it will actually converge a bit. Only if you try to apply this, you will get solutions that are really nonsense. Right? These 0 solutions do not satisfy this target map well and are not a good answer. And this averaging effect has been studied in depth in the whole deep learning field. In this case, it's very obvious. In other cases, might not be so obvious, right? This could actually happen in parts of your data where a big part that you test with looks good, but then for some other inputs, it can happen whenever the input to your network does not map to a unique output. Whenever there are multiple solutions in your output, this averaging will happen. That's what classic learning gives you. And in some cases, like in a flow, this might be very wrong. If your flow should go left or right, and you get an average, right, it might mostly go straight, which might not be a valid solution. So, yeah, for the network, it has very accurately learned the mean of the targets you prescribe. This is the expected and correct answer from a learning perspective, but it might not be the answer we want. In this case, in other scenarios, if you actually look at the underlying function, in this case, a square, directly, and you train with this in the loss, so that's actually an example of the second kind of, could call it a physics-based loss if you treat the square as your physics function, then you can check, do my generated answers actually satisfy this target function? And then at least you can make sure that you recover one side of the parabola. Most typical networks are deterministic, so we cannot easily produce two answers, but at least then, depending on your initialization, you will get either the lower or the upper part of this parabola, and then you're actually able to learn this quite accurately. So this is one aspect where the physics models can actually help to disambiguate your data, basically, to prevent this undesired averaging of multiple solutions in the data. because typically if you have a physical model, it will tell you, right, 0 is not a good answer, but we didn't need a signal with a minus or plus sign. Interestingly, exactly this aspect of having multiple solution is also one that fairly recently came up again in the field of deep learning, and that in a way really only recently started to really work. So networks that can produce a whole distribution as output, so probabilistic networks, are what effectively hides behind this diffusion modeling label. And also in this example, you can find a small variant of that. In this case, the network is not deterministic anymore. It does not just produce one answer, but it can basically learn to produce plus or minus samples here. So in this case, also being a relatively simple one, you can directly see it is a bit noisy, right? You can see these outliers along the parabola is not as accurate as the other one. Potentially, with bigger models and so on, it could be made more accurate, but it's also, I think, a good indicator of paying a price for learning a distribution instead of a deterministic single answer. It's either more expensive or requires some resources, but if you turn the learning task or the inference process into something probabilistic, you can also deal with these ambiguous targets. Nonetheless, also as an outlook, combining this with physical models is even better. We also come to that in the end. So this does not replace physics. Yes? Equidistant, these errors. In this case, the network really learns a distribution that basically has probability peaks on these two sides, and then because the data is partial, it also has gaps along the x-axis, basically along x, and there will be fluctuations of the probabilities. So it can slightly spread out the solutions, and that's why you see also some points here. And it really works with pure noise. So there should, if you sample it densely enough, well, even the training data is not perfectly symmetric. So I don't think that the distributions that you will learn will actually be in any way symmetric around x here. This would potentially be a good constraint. If you have knowledge about a symmetry like this, there's something to put in. But this is trained purely from data that is random and hence can vary. Yeah, so also this we'll cover a bit later. So for now, we actually focus on how to set up these regular learning tasks, and then these two steps will follow later on. I do want to, in this context, briefly mention typical physical equations. So also, because we want to keep it a bit general, we look at fluid-like problems, but mostly simplified equations. So you can categorize these a bit here. You can find different 1D, 2D, and 3D examples. And just to mention a few common ones, there are very basic linear PDEs like diffusion, kind of blurring processes. Berger's equation is a nice kind of a bit more advanced model that's including some nonlinearity going towards fluids. And this is basically something compressible. So in this case, you have basically a material that diffuses and moves around, but no conservation of mass. So this can push together and form shocks, but also a pretty popular model with interesting behavior. And if you then add a constraint like this mass preservation, then you actually get Navier-Stokes. So it's something that describes the motion of air. So these are typical models that we look at in the following. And yeah, also to have it on the slide explicitly, we need to distinguish forward solve. So we start with initial and boundary conditions. So we want to somehow specify a solution for a solve. For example, we start with some time t0 and then see how the system evolves over time. Whereas for the inverse solve, we're interested in a parameter like viscosity in Navier-Stokes. It could also be a geometry or even an initial state right? So this might seem a bit weird, but it's actually also a interesting question, one that we'll get back to. So if we can observe our system at a later state in time, it's a non-trivial question what states earlier in time did lead to this. So what happened a few time units ago? So it's basically really the inverse of the forward simulation, and potentially there might be multiple answers that lead to some observed state currently. So this is potentially a non-trivial one. Yeah, so I do want to also along the lines of previous questions quickly recap the basic setup for learning and introduce a notation, because we'll need that quite a bit in the next weeks. So we are assuming we have some unknown function that we want to learn. That's typically denoted by this star superscript. So we have some f star taking parameter x that produces a y, and the y star here, that's now the ground truth answer. So that is what we'd like to have. We often have this y star only as data. We might have access to running this f star, but we're interested in finding an approximation of this f star, just called f for simplicity, with a training data set that contains different input pairs. So for the x, this technically also could be attributed to the ground truth or the approximation later on. We'll just call it x. And ground truth pairs, basically collecting many xy pairs indicated by this I superscript. That's our training data set. And then we want to compute this approximation such that a certain error metric is minimized, simplest case in L2 loss, but also depending on what you're interested in, this could be something else. Could be kinetic energy or some turbulence statistics or anything you can compute given samples from your solution. Yeah, for training a network then, we're basically solving exactly this minimization problem. So we have our f parameterized by some neural network parameter theta, typically the weights of a neural network. We're computing the L2 difference between f and these ground truth solutions here as written out. And then we want to minimize this difference given the parameters theta. And this is typically a nonlinear minimization problem. Even for very simple neural networks, even without activations, as soon as you have multiple linear layers, this turns into a nonlinear problem. So this is typically difficult to solve. We usually have large degrees of freedom. So these theta, these parameters in networks are typically large. That has been shown as one of the kind of hyperparameter regimes where this deep learning works nicely. Classical machine learning often worked with very small solution spaces, but turns out if we have very large ones, in a way that makes it more well-behaved. Drawback is that we have many plateaus. So for the energy, there are typically large regions of changing the theta where we don't see large changes in the loss. We don't pay attention. This kind of gets stuck. So it's not easy to solve these. But in a way now with Adam and co, we have pretty powerful tools to, and the stochasticity, the randomness with perturbations being a very important ingredient, to find pretty good solutions for learning problems like this one. Yeah, based on this formulation, I do want to make a few comments on the basic setup. So traditionally for machine learning, you have this distinction between classification and regression. So what's finding out for the physics problems, I think regression is the key task. So we're dealing with continuous x and y. Right? These are, for example, temperature or position or something where we basically assume it can vary without any noticeable steps. Of course, later on we're in the computer. We will have discrete steps, but in terms of the target, these are continuous variables. We'll actually look at slightly different regression tasks because we will not only have the neural network here in the picture. This is one way to combine it. Just to write it out, we might have some solver, some physics operator, typically denoted by this p, in the picture. This could actually be alternating in different ways, but to simplify it a bit, can imagine that we're basically calling another potentially complicated function p on this f, and then we want to minimize the whole thing. The important message is a bit, this really changes the picture. So potentially we're not just dealing with the nonlinearities and the difficulties of the network, but we're involving the challenges of physical models that need to be taken care of at training time. Yeah, also looking ahead a bit, also maybe intuitively, one of the problems, as mentioned before, are basically regions that are difficult to optimize, like these saddle points, right, where we don't have a good direction. And the physics typically can introduce that even more. The physics will distort our landscape and distort the loss values and potentially make some parts of our landscape even steeper or other parts even flatter and larger. And dealing with this uneven scaling is one of the challenges in this context. All right, so how does the classic supervised training go? Right, we'll call this supervised to distinguish it from training with physics constraints or losses. So there are some obvious disadvantages. Basically, the physical model does not play a role, and the accuracy and also generalization, kind of the region where you can use this, is dependent on your training data. So if you have a collection of data, these XY pairs, and it covers a certain parameter range, usually your model will not do a good job if you put in an X that's far beyond this parameter range. So you can typically, if your training data is good, you can fairly safely interpolate. Although even there, from a physics perspective, if you have almost discontinuous or very sharp changes in your behavior, if those are not well captured, you might have trouble. And also intuitively, if you have X that are just very different, right? If you train for motions between 1 and 2 meters and you input a 10 or 100 or even larger ones, potentially this will give problems. Or also, in terms of generalization, if your data does not vary certain parameters. Again, flows, if you have training for airflow in rooms and you always train with the same geometry, the same shape of room, and then you put in a new one after training, right? Your network, that's what it's good at, basically overfitted to exactly the shape it had always seen in the training data. This will not work on new geometry. So if you want to change a geometry, it's important at training time to vary the parameters you want to vary later on at inference time when you actually want to use it. Otherwise, this is pretty much guaranteed to fail. I will show these kind of the main algorithms of the learning setup with these schematics. So this is what I want to also introduce here for this very simple case. So we have an X and an F that produces our Y. We have a loss, and then for training, we actually need to compute a gradient with respect to the input. So we're taking the output and this loss, backpropagated, that's what's happened in the backprop step, and then track this change or the signal, how the output would have needed to change back to the parameters theta in our network. So basically the gradient of f with respect to theta in order to run the training process. And yeah, later on, this looks very simple, but later on, right, we want to integrate other components and pieces here, like a numerical and physics solver. This is actually quite, this purely data-based process is quite attractive from a pure or traditional machine learning perspective. So there are people that are big fans of this because it basically avoids any inductive biases. So you're really just starting from a huge data collection. You don't need to manually tweak much, maybe apart from hyperparameters or typically quite a few knobs to control or at least keep in check. But in a way, you're training something purely based on the data. So right, this is the ML dream, right? Ideally you don't need any human input. If this would work, you just give it a lot of data and then you get a working model. That's definitely attractive on some fronts. if you're coming from the simulation of physics perspective, this is horrible, right? It basically does not use any of the knowledge we might have about our data, and just relies on the learning process to take care of everything. So especially in the past, I think many people from the simulation and computational physics community were horrified at this, because we have, for many scenarios by now, pretty good understanding of what things should do, like Navier-Stokes, or like all the experiments and analysis we have. And all this would not play a role if we directly just train with the data. So yeah, that also motivates a bit again, right? Maybe we can bring back some of that knowledge into the training and improve it, do better on this front by using the knowledge we actually do have. But from a machine learning perspective, it also has some attractiveness to not rely on any human biases. Also, the argument there typically is that if this in a way restricts your working range, right? If you know about something, you might be able to work with it, but if you don't know it so well, then if you try to fix it or without limited understanding, maybe we're putting in the wrong biases. Maybe that could prevent us from finding the right solutions. And that's, of course, something we want to avoid. I think, actually, especially in our environment by now, I think many aspects are very well studied, and there are quite a few things that we can safely include without negatively impacting the learning process. Yeah, so this example I had on the slides before, these airfoil examples in this web book, you can actually find a Jupyter notebook that runs this back to front if you want to give it a try. So this uses a unit structure to learn these RAND solutions, and feel free to experiment. This is also not too costly to train, despite being a spatial solution. The notebook is 32 by 32, but still has a fair number of degrees of freedom, and I think the typical parameters around 200, typical network parameterization on 200,000 parameters. So it's a decent neural network, but a very good example of this purely supervised process. One other thing that I do want to mention here, I've just talked about getting an X producing one Y output. For many phenomena, for many things in nature, we might be interested in actually more than that, in a time evolution. So a sequence of states or something that tells us how things actually change over time. And nicely, that still fits into the same picture. So even if we're given time series data, so we have changes over time denoted by the superscript here. This could be some solution U over, in this case, n steps after some initial step. We can actually turn this learning process into a time series learning by treating a certain input, a UT, as the X, and then aiming for the learning task to predict U at t+1. Right? So if we basically just train a network to take care of advancing our solution from one time step to the next, this can be treated as just like before, training a network now just with these outputs, inputting a time step, and then once things work, we actually have a network that hopefully has learned the time evolution of our system, and that we can use given some U0 to predict what happens in the subsequent time steps. The big difference here is that now we're not dealing with one call to our network, but we might need to call it n times. So every time we call our network, we're advancing it by one time step. And to get the whole solution, for many practical scenarios, that might be hundreds or thousands of calls. And this is actually an interesting challenge, because it means we recurrently need to call this network, and errors will accumulate. So this is also in the learning field its own kind of challenging sub area. Often that's called autoregressive rollout, or recurrent neural networks fall into this area. And the challenge here is that if you think back to what I just said on the previous slide, right, you're always training from t to t plus 1. The network is trained for these single steps. However, what we want to have is a network being applied hundreds of times. Sounds similar, and if this one step works perfectly, this should be the same. But we have errors, so in practice it will not be the same. We have approximation errors. This f we're getting is typically, even if it's trained super well, on some level, right, on the level of discretization. It could be tiny, but we always have some discretization or some small error. And then if we want to apply our network often enough, these errors will grow. And how they grow can then very strongly influence our solution. So this can actually be looked at from a dynamical systems perspective. So dynamical chaotic systems are often looked at in terms of an attractor. So if we do exactly this unrolling of our solutions over time, for many classical systems, we can study how the solution, we call it this U, actually converges to a certain stable states or solutions that, if we do things right, also are the ones we want to have in our physical systems. Those are very famous examples you might have seen, like these Lorentz systems that oscillate around different points and then have attractors for certain locations that they typically converge to. And this behavior, these attractors, come from applying the physics operators many times, right? It's a kind of limit behavior or limit viewpoint on the dynamics of this physical system. And now, if we look at the neural networks from this perspective, we typically have a true attractor that comes from the P, from this physics operator, our real solver, and we are replacing that physics solver with a neural network that has some approximation error. So in a way, inevitably, these attractors that you get from a neural network will not be the same that you had in your physical system before. And in a way, probably not too surprising, but because this depends on how often you basically call this f, how long you look ahead with your operators, especially this one step that we're training with is a problem here, right? This is potentially, if we're interested in thousands of steps, this is very short. So obviously, what you probably need to do is you need to train with more of these steps. And yeah, this is in a way a classic data shift problem, because in implication, or one of the reasons for that happening, is if we now have an f which is not equal to our p, and we call this f many times, inevitably what we get out will look different than what we pre-computed, our training data. I hope that's intuitive, right? So we have an approximation, even if the error is tiny. If we call it often enough, at some point we'll see a difference. The network was always trained for outputs of our simulator, the p. So these data points, the U's we'll get from our f, from our approximation, will be different, will be guaranteed to be different to some extent from the training data. And basically, now we have a case where we are running our network on things it was not trained for, simply by looking at this time evolution. And that can cause all kinds of problems. Worst case, within a few calls or f, things can blow up. If you're lucky, you can just slightly drift, but this is a data shift, what you would call it in machine learning, because the network is later on applied to shift the distribution or data that's different to what it was trained on. And basically an obvious fix is here to avoid this shift by showing the network more of these different use of the different data at training time. Yeah, but because it's about time, this is also an example where we can illustrate this evolution and these problems a bit. So this is a relatively simple example of a flow around obstacle here. So flow coming from the left-hand side. These are actually all, to mention, pretty good models, so they don't blow up immediately. But yeah, now it's playing. what you can see here is the reference at the top, and then one network, in this case an F&O, being trained on the same data as another version unit here that was actually trained with more of that time evolution. And now we can start to see there's some weird patterns that start to show up here, and this is now showing several hundred frames, but eventually this middle version would actually blow up. So you can see how the errors, the repeated evaluation of the learned operator, actually start to influence the solution, and the network has never seen these weird patterns, probably mostly or especially the ones near the boundary, and then it starts to reinforce that. Basically it doesn't know how to handle these, and then eventually strongly diverges. So in this case it's relatively slow to see, but this is a typical result of this simple training process. Yes? The color. So the question was what the red and blue encode. This is in this case the vorticity. So it shows the left or right rotations of the motion of the flow. So that shows you a bit how things rotate left and right. You can see it a bit. So this is a nice visualization for these flows. In one picture, you can get an estimate of the 2D motion here. Right. Yes. In this setup, the learning task was actually to produce the motions, so the velocity vectors on this whole array. So this, I think, is something like 64 by 128, and the network gets one state and it's supposed to predict the evolved version for the next time step or across the whole field. So this is a typical learning task in this context. But this is also what a normal simulator would do. Normal fluid simulation advances in exactly this manner. It takes one state from that, computes the time evolved solution. Yeah, so we get into fixing this later on. This time dimension or the challenges are an interesting aspect. Right? You call it unrolling, basically these multiple iterations. But just to mention, so even if we just look at learning tasks, f of x being y, potentially this extends to time and has some interesting challenges. Yeah, for today, I do want to mention a few best practices with the supervised training. So even if we're looking at neat and complicated physics models, it's really important to always start with these supervised training approaches. Right, I hope many of you are familiar with this, but also when testing, or important reminder maybe for the exercises, but it's really important. Always make sure you overfit first. If you cannot overfit your model to a single data point, then something's fundamentally wrong. Then there's no point in going on, right? It's always an important step to start with one data set point. Make sure your network can find a solution. If that doesn't work, that means there's some either an obvious bug in your setup, or it might be something non-trivial where the solution cannot even be determined from your inputs. We've had these cases. Even if this code is working, your setup might be so ill-conditioned, so ambiguous that the network cannot predict the output based just on the input. It's also important feedback. So it's a good idea to double check that you can get very low errors, and also if you make the network large and learning rate small enough, you should be able to basically bring down errors up pretty much arbitrarily for these one data point scenarios. Yeah, once you've had that working, then you can make it better, look at larger training data sets, look at evaluations on test data, right, on potentially a bit different data than the one from training. I also do very strongly recommend to always check or always print the number of parameters in your network. In a way, in this field of computational physics, we're always competing with solvers. So it doesn't matter whether your network has 10 million parameters or 100. That will make it slow or fast. And potentially, or ideally, we want networks that are as small as possible, that give us a solution without being very wasteful. So that is a good parameter. Also, it might indicate whether your training data is big enough, right? If you have a model that uses 10 million parameters and you have a data set of 100 small samples, then that might be problematic. Or vice versa. If you have a huge data set with millions of degrees of freedom and you try to fit it with a tiny model, also probably not going to work well. So there's a nonlinear or typically unknown relationship between these two, but yeah, at least a factor of 10 between the two is recommended, and they should be in similar orders. They should not be completely unrelated. Hyperparameters are also important to adjust. What's the most important one? Yes, learning rate. Yes, thank you. Exactly. The learning rate is the most crucial one. Also happened often enough. You think it's not really working, but try a smaller learning rate. Suddenly it might start behaving better. Unfortunately, it also depends on the data. Right, 10 to the minus 4 is a very good one. Many frameworks are tuned to that, but especially if you don't have normalized data, you might need different ones. Hyperparameters also might include tweaking activation functions and so on. So that's a good later stage to check here. And then once all these basics are working, then it's actually a good point to maybe go for larger scenarios with more and more data, more generalization. And also physics models is a good step after this. If this basic learning does not work, then again, the physics will typically not help out much on top. Yeah, so I do have a quick summary here on the slide. So there are also pros, definitely. It's by now these methods for training with supervised networks are quite reliable. There are many hands-on experience reports, and you find typical parameter ranges, like the 10 to the minus 4 is very popular. If you normalize your data, that's probably a good starting point. So this is, it also typically, it works quite well. So that's definitely a plus. It's by now quite established, and it's fast. So also there's good support by now in many frameworks. You do get GPU support from these basic architectures. You try to bring in physical models that might be more tricky to do. So it's definitely a good starting point. Yeah, the generalization is a problem. So that is an aspect that we'll also get back to. Intuitively, if you set it up right, ideally you can rely on this solver or this coupling with physics to take care of generalization, at least have larger shifts in your data distribution. Then the network puts something on top that is applicable over wider ranges. So by finding the right combination, you can actually typically improve the generalization of your network. Whereas if you rely on data, you need to make sure that your data covers all possible variations of inputs that you're interested in later on. Yeah, there are these fundamental problems with a simple deterministic supervised setting. Right, the averaging over multiple solutions is one that is also can be fatal, and the pre-computed data, I've mentioned this data shift problem over time, can really hurt certain applications. The interesting part here also for the time evolution is that if you think back about the example, right, we're getting the changes from the network. The network produces something that after 100 calls to the network looks different. But before training, we don't have the network. So this kind of data we cannot pre-compute. So if you rely on pre-computed data, aspects like this you really cannot train for. Yeah. Nonetheless, the foundation for the next weeks to come, and as such, supervised training is an important starting point also for the exercises. I want to wrap up there for today. Next week, I do want to talk a bit about architectures. It's also a pretty common early on choice that you need to make when using these, and it has some implications. So next week we'll look at architectures and then start with the physical models, if they are. Yes, that question. Yes. Okay, so the question was how the state of the art in deep learning and neural networks compares to the state of the art in numerical methods, right? And classical solvers, exactly. It's also a very good question. So I can say that in general, if you don't pay attention, actually to start with the positive ones. So I think by now we have methods that you can train networks that give you any accuracy. Right? So if you especially if you think about large models, if you have enough data, if you set it up right, you can pretty much get any level of accuracy that you might need for an application. And we have huge models. Not many companies might be able to pay for training, but I think you can get by now pretty much arbitrary accuracy. On the other hand, if you look at things like ChatGPT or models like this, they're also huge. They are not cheap. So if you then compare whether the learned solve you get out of these has any benefits over the traditional one, things start to become less clear. So unfortunately, they can be accurate, but if you don't pay attention, they can also be slow. So it's also a caveat or a warning. If you use neural networks and learning, there's no guarantee that it will be fast. This can be slow. If you have a huge transformer that sequentially processes a long input sequence, companies like OpenAI have good backends and the infrastructure to process this quickly, but it involves a huge amount of computations. And then it might actually, if you're unlucky, be faster to just run the classical solver because of the gigantic workload of your neural network. So hence also the comment early on to look at the parameters in the architecture. There is a potential benefit, but if you don't pay attention, it might disappear or worst case be slower than a classic one. Yeah. I would argue that for the vast majority of cases in the computational physics setting, it is exactly this, an accuracy performance trade-off. We have solvers. It's not easy, but if you take SuperMOOC or some large supercomputer and invest enough resources, you can probably get the right expertise. You need to set it up. It's also not trivial, but you can probably get super accurate answers for many simulated problems. It's really more the question: can we get accuracy we're interested in faster with a neural network? And I think also from my experience, there's no magic involved, but by trading some generality, so having something that's a bit more specialized, we can actually get there faster. And for many applications, that is worth looking at, right? For many applications, if I want to solve airflows in this room, I might not be interested in compressible explosion solves or so, or temperature or chemical species, but I want something maybe that just very quickly gives me the kinds of solutions that I'm interested in. And this kind of generalization is tricky to do with traditional solvers. So I think it is a classic performance accuracy trade-off, but a very interesting one. All right, thanks so far. See you next week.